Let's get started, I guess. There's like 8 people here. A standard end of semester lack of attendance. Yeah, you're right. Maybe I should give you all a bonus. I think there's only 4 lectures left, including this one. And next week we have an open lecture, so I don't have any planned topic. So if any of you would like to see a particular topic that we haven't yet covered, please feel free to suggest on Piazza or the anonymous forum. One thing I was thinking, because this semester the big PaLM model came out by Google and many other of these large language models, it might be useful to have a lecture on what's known as the scaling laws of large language models. So seeing how many parameters do you need before this kind of behavior becomes present in one of these models and so on. But I am open to other things, so feel free to suggest. This week we are kind of taking a different direction and focusing on parsing. So parsing is the task in which we have some text and we want to convert that text into some sort of structured representation. Today we'll be focusing on syntactic parsing. So given a sentence, can we obtain a tree-like representation of the that encodes kind of the grammatical rules that are used to form that sentence. On Wednesday, we'll be talking about semantic parsing, which is very useful for tasks like question answering or interfacing NLP with robotics. So if you want, for example, to command your robot to do some task in natural language, that robot probably only understands like some very simple formal language, right? Like go right or go left for this number of steps or so on. So how can you convert your natural language utterance into something that the robot can understand and execute? That's Wednesday's lecture. So today, as I mentioned, we'll be talking about syntactic parsing. So the specific setting is we're given a grammar, and we'll talk exactly about what a grammar is. But given a grammar which tells us the rules of the language, how do we use that grammar to obtain a parse tree structure of a sentence? So as an example, here we have the sentence, a mouse eats a cat, and we have a tree-like representation of the sentence, which is something like what we would want to obtain from the methods that we'll be discussing in this lecture. So you can see here that this is a binary tree. The lowest level of the tree, the leaf nodes of the tree, correspond to the words of the sentence, and every other node is representing what's known as a non-terminal. So this D here means this is a determiner, this N is a noun. So the second level of the tree generally corresponds to parts of speech, of single words. And then you can see that the higher up levels of the tree are more phrase-like or even sentence-like in nature. So this noun phrase corresponds to a mouse. This determiner and noun merge together. This NP or noun phrase exists because there's a rule in the grammar that says you can form a noun phrase by putting together a determiner and a noun. Similarly, this verb phrase spans the entire eats a cat. So eats is the verb of this verb phrase. A cat forms this noun phrase, which in turn is formed by a determiner and a noun. Finally, S usually represents a sentence. So you can get to a sentence in a variety of ways. One way in a simple sentence is to just combine a noun phrase and a verb phrase together, which is what we see here. So it might seem like a fairly simple task if you're given all these little rules, like noun phrase can be formed by a determiner and a noun. It should be pretty trivial to form a tree like this, but it actually turns out to be quite difficult given the size of these grammars and the length of some of these sentences. So we'll look at an efficient way to obtain these trees, and then we'll talk about how to get the most probable parse tree if your grammar has probabilities associated with each rule. And we'll talk about some other cases towards the end where maybe you don't have a grammar, what do you do then? Or you don't have the probabilities for the rules, and so on. But before we start, it's important to talk about why we care about parsing in the first place. So historically, and this means like 2012 when word embeddings and then contextualized embeddings and then things like BERT and GPT-3 and so on were introduced. Before all of these neural models were available, we generally would solve NLP tasks by taking a text, extracting features from that text that we knew are predictive of some sort of label. So, for example, if I'm doing sentiment classification, it might be useful to know, that this phrase exists in the sentence and it's a verb phrase and it has this kind of sentiment generally. Things like part of speech tags or phrase types were always very useful for, like before we had models that could actually learn those kinds of things by their self-supervised objectives like we see in BERT, for instance. So that's the historic reason. Nowadays, if you have a new NLP task, no one is going to recommend that you run it through a parser and extract all of these like different features that were common pre-deep learning. They would just say, use BERT, right? That's probably a good enough suggestion. However, we've already seen some instances of parse trees being useful for other kinds of things, not necessarily improving performance of a neural model, although there are some works that focus on integrating these tree structures into neural networks to get improved performance. I will say that it's still not clear if those methods are effective, especially with increasing scale of the models. People might have shown that for a small neural network you can get some gains by incorporating tree-like structure or features from a tree into the model, but with something like GPT-3 or the POM model, I suspect it's negligible if you get any benefit or not. However, there are other use cases. So for example, if you have some text and you want to extract key phrases, if you want to extract, for example, verb phrases, which are commonly associated with actions, there's of course, you could probably design some neural network tagger to do this, but it's simpler to just run a parser, which will detect verb phrases for you, and you can go ahead and extract those yourself. So anytime you have a setting where you want to extract phrases from text, parsers are very useful. We talked when we were discussing probe tasks about these syntactic probe tasks where you can, for example, measure whether or not your neural network has learned like some sort of tree structure. Does it kind of induce this tree within the parameters of the network? And maybe that's why these external parsers are not useful anymore. So we talked about one probe task where we would see whether or not the neural network model had encoded distance between two words in a tree or depth differences between two words in a tree. So yeah, in these kinds of probe tasks, it's very common to have a stronger connection to more like linguistic-y models like a parser. And related to that, parsing is also very useful for psycholinguistics-based experiments, which are trying to understand how humans learn language, not models. But if you're doing that at scale, it's probably good to use a parser to understand the tree-like structure of some of the sentences that you might be showing humans and doing all sorts of experiments on. Okay, so let's take a look at some concrete examples of why it is often important to know the syntactic structure of a sentence. basically natural language has a lot of ambiguity, right? And there are a couple examples on the slide. So I shot an elephant in my pajamas. Does the pajamas, like who's wearing the pajamas? Is it me or is it the elephant? There are scoping issues, right? So Southern food store. Does this mean the store is in the South or the store is selling Southern food? The tourists objected to the guide that they couldn't hear. So are the tourists just like generally objecting to this guide, or they're telling the guide that they can't hear the whatever they're saying? And you know, there are many other cases like this, and it happens all the time. So you might think, you know, these are like cherry-picked examples, but people, when they're writing, usually aren't very clear on, you know, which particular meaning they intend. They might intend a certain meaning and are not aware of all the other meanings, especially in more informal settings like Twitter, where it might be hard in general to understand what someone is saying. So there are also parsers developed for things like Twitter, which have their own grammars and own models. So you can check that out if you're interested. Actually, one of our NLP faculty, Brennan O'Connor, developed some of these NLP tools for Twitter specifically. Okay, so let's get started with the basics of parsing. And so the first thing that you need is a grammar. And this is a grammar that essentially tells you, you have some rules in this grammar that are of the form a non-terminal node, which is, you know, one of those higher level like phrase types or part of speech types. How can you form those from your terminal nodes? So this has a bit of jargon in it, but in our setting, the terminal nodes are associated with the word types in the vocabulary. So like in our example, a cat eats a mouse or whatever, a mouse eats a cat, those would all be terminal symbols. And a rule in this kind of grammar would be of the form, you know, determiner is formed by the word a or the word the. So you have this set of rules, which is of the form non-terminal on the left-hand side. It is created by some combination of either non-terminals or terminals. So you could say, you know, I can form a noun phrase by combining two noun phrases together, or I could form a noun phrase by combining a determiner and a noun, or whatever. There's also the start symbol, which is the goal in parsing, is we want to be able to combine all these rules together to get a start symbol that spans the entire sentence. If we can get to that point, then the start symbol, and if we follow down the path that it took to expand into the whole sentence, we have come up with our tree structure for the sentence. So let's take an example. It'll hopefully be more clear. So we have this simple grammar here with three rules. So the start symbol, S, is formed by combining a noun phrase and a verb phrase. So you can see here that there's a non-terminal on the left-hand side and two non-terminals on the right-hand side. Here we have a different type of rule. So NN, it represents a noun. So this is kind of like a part of speech. And here we see the non-terminal is formed by a terminal symbol, dog. Dog is a word in our vocabulary. Finally, here we see this other rule, a noun phrase is formed by a determiner, an adjective, JJ represents adjective, and a noun. So we have these three rules. And in order to use the parsing algorithm that is the one that we're going to talk about in this lecture, and also the most popular used one in all implementations, the CKY algorithm, we first need to convert this grammar into a specific format called Chomsky normal form, in which each rule is either of the form of the first rule here or the second rule here. So there cannot be instances where there are more than two non-terminals on the right-hand side. There can't be instances mixing a non-terminal and a terminal on the right-hand side. This is done to ensure that the tree that you get finally is a binary tree. So we don't have these like three or more branches from a single node. That would make the algorithm more complicated. So this Chomsky normal form grammar is easier to explain by example. So if we take our previous grammar, the only rule that violates this constraint is the third rule, because it has one non-terminal that's formed by three different non-terminals. It's very easy to convert this into the normal form. All you have to do is introduce an additional non-terminal, say here x, which is going to correspond to two of the non-terminals in the first rule. So here, x, this new non-terminal, is formed by a determiner and an adjective, and then this noun phrase is formed by an x as well as a noun. So you can imagine writing some sort of simple pre-processing script to convert all of your rules that look like this into these binarized rules. Just a bit of necessary pre-processing that we have to do in order to use the CKY algorithm. All right, so given a sentence and a grammar that is in the CNF form, our goal with parsing is to search through the space of all possible parses for that sentence to find a valid parse, which means any parse that begins with the start symbol, the start non-terminal, the S1, and spans the entire sentence. We might also be interested in finding every valid parse of that sentence, because maybe there are multiple different interpretations of that sentence that we're interested in ranking or something like that. Finally, we might be interested in the most probable or most likely parse, given that there are many different possible tree structures for that sentence. So there are two approaches that have been used by, there is a lot of research in parsing before 2012, and still it continues to this day, but it's more like neural parsers, not feature-based ones. But there have been two approaches historically. There's a bottom-up, which involves starting from the words of the sentence and trying to combine them in a way that eventually you get to the start token that spans the entire sentence. And there's also top-down. So you start from this S symbol, and you keep expanding down until you're able to construct the sentence. So can anyone, if you think about this, are there any pros and cons of either one of these approaches, the bottom-up or top-down?
Seems like top-down have a really big search space. Like you're kind of unconstrained versus the bottom-up, you kind of have to read nodes are set, and then you just follow the rules.
Yeah, so there are trade-offs for both approaches, right? In the top-down approach, you are guaranteed to have a valid parse, which is good because you're starting from the start symbol, but there are potentially thousands or tens of thousands of rules. So you might form several trees that have other words than the ones in your sentence, or are not spanning the entire sentence, and you're not guaranteed to get a tree that contains all those words in the sentence. So you might explore a lot of different hypotheses before finding a valid tree. On the other hand, in the bottom-up approach, as you say, your leaf nodes are fixed, so at least you're guaranteed that your tree is going to have the correct bottom level. On the other hand, you might start combining things and find, at some point you just don't have a rule that will get you to the start symbol and span the entire sentence. So there's a trade-off. Most parsers are bottom-up for the reason that you mentioned. The search space in top-down is very large, so you have to use a lot of pruning and heuristics in order to make it manageable. Okay, so we will talk about a bottom-up parser now called the CKY parser. It's named after the initials of the discoverers. And it can be used with both the grammars that we've just described as well as probabilistic versions of these grammars in which each rule is associated with a probability of that rule's occurrence. So here's another example of the ambiguity. I shot an elephant in my pajamas. How he got into my pajamas, I'll never know. So there's like two different valid parses of this sentence, and This one is choosing probably the less probable parse with that any human would choose, at least. Okay, so let's take this sentence, I shot an elephant in my pajamas, and use it as an example of the algorithm, this bottom-up parsing algorithm. So here we have this grammar that's already in Chomsky normal form. Remember that a requirement for running a parser is having a grammar in the first place. And there are many ways in which you can obtain these grammars, which we'll briefly talk about later. But this lecture will primarily focus on, given a grammar, how do you get the tree, which is the task of parsing. So here we have our non-terminal rules on the left. So remember, these are of the form non-terminal is formed by two other non-terminals. And then we also have these rules which are one non-terminal formed by a terminal symbol. And remember, all the terminal symbols are the words in the vocabulary. So you can see that there's some ambiguity in this grammar already. I, for example, the word I can make a noun phrase, or it can also make, I think this is personal pronoun. So there's some, like, both of these could be components in a valid parse of this sentence. And over here, you see that there are multiple ways to form noun phrases. So there's determiner followed by a noun phrase, or noun phrase followed by a prepositional phrase, or a personal pronoun followed by a noun phrase. And then there's many ways to form, two ways here to form verb phrases. And remember that this is a highly constrained toy grammar. Most grammars for real parsers are much, much larger than this and have many more rules. And you can imagine that most of those rules are of this type, right? They're just like part of speech to word. So the bigger your vocabulary, the bigger your grammar. Okay, so the first thing we do in the CKY algorithm is build this chart. And so you can see that the chart is spanning the entire sentence. So how you interpret this chart is that there are different levels of the tree. So these cells on the leftmost edge of the tree represent the leaf nodes, essentially. So here I would try and fill up any rule that forms the word I. So I have two such rules in my grammar. This cell is associated with the word shot. This is associated with the word in, and so on. So the very first thing I do is fill up this last level of my chart with all of the non-terminals that produce the corresponding leaf node. So remember, I, in our grammar, we could produce I in two ways, with a noun phrase or with this PRP. And so we have two different non-terminals that go in this cell. For every other word in the sentence, it can only be used to form one non-terminal. So this, like, past tense verb, this is a determiner, a noun phrase, and so on. So this is an easy part of the process. You just have to look up what each terminal is associated with and fill in the corresponding cell. Now, the second level and all subsequent levels become a little more complicated. So here, this cell spans the phrase I shot. So now we're looking for any rule in our grammar that when we combine the non-terminals in each of the spanned cells, so this cell and this cell, will form another non-terminal. Eventually, we want to get to a point in this top right cell where we are able to form an S, because this cell spans the entire sentence. So just as a bit of, to make sure you're following along, what does this cell span? What words in the sentence are spanned by this cell? If this cell spans I shot, what might this cell span? Yeah. So no, so the way to interpret this is if you look at the row here, the row starts with shot. So this phrase is actually spanning shot an elephant in my. Of course, shot an elephant in my probably is not associated with any sort of non-terminal, right? Because it's kind of in the middle of this prepositional phrase, so we might not have anything in this cell. But yeah, that's the way to read this chart. So this cell here spans the text from the end of the row, like the beginning of the row, till the cell itself. So like the column of the cell itself. Okay, so this cell here spans I shot, and so we're looking for a combination of any of these three non-terminals in our grammar that forms a new non-terminal. So I would look for NP VBD. I see no NP VBDs. I see a VBD NP, but the order here matters, right? Because this means a verb followed by a noun phrase forms a verb phrase. We have here a noun phrase followed by a verb, like a past tense verb. So I don't see any rules here that allow for that combination. I also don't see any that start with PRP VBD, right? That on the right-hand side. So I can't form any sort of non-terminal with my grammar that spans this phrase, I shot. So now we'll move on to this cell, shot an. For shot an, there's only one possibility to consider, which is VBD determiner. So I look here, I see no VBD determiners on the right-hand side, so this is also a bust. So I move on now to an elephant. This, I have a determiner and a noun phrase, right? So I look here and I actually do have this rule. NP is formed by a determiner and a noun phrase. So I can fill this in with finally a non-null symbol. I can get a noun phrase for an elephant. And you see that makes sense, right? An elephant is a determiner followed by a noun. And so I can fill in the rest of the second level by following the same logic. And I find here this cell that spans my pajamas also is producing a noun phrase because this PRP and NP is part of my grammar here at the bottom. Okay, so any questions so far? Yeah. No, we'll see how that works in the third cell. So basically, whatever you're combining has to span all of the words in the cell that you're trying to fill in at this point. So in the second level, we could only ever combine like two adjacent cells, but when we get to higher levels, there are many more possibilities that can be combined, as we'll see. Yeah. Oh, sorry. Yeah, only continuous spans. Yeah. Yes, so you only are allowed to put something in a cell if there is a rule that combines two non-terminals from the levels below that span the entire phrase that associated with the cell that you're at. So this was like kind of easy in the second level because there's only ever two cells that you can consider. Well, let's go to the third level and it'll be more clear. So here we're looking at the phrase, I shot an. There are actually two different ways to form this phrase. The first way is to combine I, which is spanned by this cell, with shot an, which is spanned by this cell. And we see here that there's no way to form shot an in our chart, so there's no way to form anything in this cell with I and shot an. Similarly, there's another way to form I shot an. So we can take the phrase I shot and see if anything forms that phrase, and then combine it with whatever can form an. So you see that there's two possible ways now to span this cell I shot an. We have to consider both possible ways. In this particular case, neither way results in a valid rule, right? Because this null symbol is not part of our grammar. So this cell also becomes null. So let's try this cell here. Shot an elephant. There are two ways, again, to form this phrase. I can combine shot with an elephant. And you can see that this looks quite promising, right? Because I have a verb, VBD, combined with an NP. And we see that I actually have this rule here. VP is formed by a past tense verb and a noun phrase. So I can apply this rule to put a VP into this box. There's another way, though, that I also have to consider, which is shot an, so this cell here, with elephant. But we see that that's not possible, right, because this is already null. So I am able to apply this rule and form this VP here. So now I can similarly do all of the third level of this chart, and we see here that we put in a PP. So this cell spans in my pajamas. And we form this by combining in, which is associated with this non-terminal in. This is reserved for like prepositions. And I'm combining this with this NP, my pajamas. So if you look in our grammar, there's this rule, PP is formed by in and NP. So that's what I've applied to get here. We see that the other option, in my, combined with pajamas, can't be used because there's a null here. Okay, so everyone following along? All right, so things get more complicated as you go up the tree because you have to consider more split points of the phrase. So for the fourth level, our options here are, now we have three options of split points. We have this NP combined, which is spanning I. We could combine it with this VP, shot an elephant, right? Because that whole thing now forms I shot an elephant. Or I could combine this PRP with this VP. I'm not sure if that's in our rule set. It's not. So there's actually a way to form an S in this cell, like a full sentence, which makes sense because this is the phrase I shot an elephant can itself be a sentence, right? It's a noun phrase combined with a verb phrase. So that's one thing I can do. And if you look at these other two cells here, they're both null. So there's nothing else I can use to form a non-terminal in this cell. So I have an S here, but of course this doesn't mean that we're done because we still have the whole rest of the sentence to go. So in the fourth level, if we look over here, I've formed a noun phrase, elephant in my pajamas. So this is formed by combining this noun phrase associated with just elephant with this prepositional phrase associated with in my pajamas. As you can see, I can form a noun phrase. Wait, oh, is that how I formed this? What is the right? Oh, yeah, this rule here. Noun phrase is formed by a noun phrase and a prepositional phrase. I use that rule to get this noun phrase. Okay, so on the fifth level, these two cells, I couldn't form anything with any of the split points. This cell becomes quite interesting. So here, this cell spans an elephant in my pajamas. And there are many ways to form things with this particular cell. So let's start with an elephant in my pajamas. So an, I have a determiner. Elephant in my pajamas, I have a noun phrase. And so determiner plus noun phrase, I can form a noun phrase. So I can at least form a noun phrase with that one split point. But now we also have to check out this, an elephant and in my pajamas. So an elephant is a noun phrase. In my pajamas is a prepositional phrase. So now I have this NP and PP, and now I can form another noun phrase using a different rule within the same cell. So here, I actually have two different noun phrases that I can form. So you can see now the potential for having multiple valid parses of the same sentence. Here, regardless of what I form up here, I can use either of these noun phrases and have a different parse tree for the whole sentence. So this kind of motivates why it's important to associate probabilities with these rules. So ideally, I'd be able to pick one of these and continue with it up the tree instead of having to consider both of these. All right, so here we have the same kind of issue. This cell spans shot an elephant in my pajamas. So here I have two options again, two valid split points. This VBD combined with a noun phrase can form a verb phrase. So I can actually form two verb phrases using this split point. I can do VBD NP1 or I can do VBD NP2. So already I have two different verb phrases that can be formed. And then I also have this split point, this verb phrase associated with shot an elephant, combined with this prepositional phrase in my pajamas. So VP, PP is also a rule here. It's associated with a VP. So I can form three different verb phrases in this cell. So things are getting a little complicated, and you can kind of see what happens up here. So at the root node of this tree, this is where I want to form an S. I have an NP that can be combined with any of these VPs to form an S. And I also have this S. I shot an elephant, and then I have this PP in my pajamas. Unfortunately, there's no rule that combines S and PP together, so I have three different S's that I can form for this sentence. And you can see how this kind of all stemmed from having these multiple noun phrases and having two valid split points up here. Yeah. So you mean in this cell? So you're saying, can we have more than these three VPs? Yeah, so there were three VPs in this cell that we showed. We formed them by combining this VBD with each of these two noun phrases. So we got two VPs from this split alone by using both of the NPs in this cell. Of course, we can't use any of these other NPs because they wouldn't span the whole text, right? So if I wanted to combine this verb with this NP, I would be skipping this word "an" from the span. So remember that we can only combine things that span the entire part of the sentence that is associated with this highlighted cell. So it has to be like contiguous span of words. And yeah, did that answer your question? Okay. Any other questions? Yeah.
So in the end, we end up with three S's. Does that mean there are three interpretations of the sentence?
Yeah, so the question is, we have three S's in this root. Does that mean that there are three interpretations of the sentence? Yes, there are three interpretations as defined by the grammar that we were using to parse this sentence. And now that we've gotten to this point and we understand how, given a grammar, we can use it to get these different interpretations, now we can start talking about, well, how do you actually choose between those interpretations? So that's what we'll do next. Yeah.
So, I shot an elephant in my pajamas. I was in pajamas, she was or the elephant was in pajamas. Do you know the, like,
Oh, I see, you're trying. I am actually not sure because this grammar synthetically just made up to show that there are multiple possible parses. I don't know what the third parse represents here, but yeah, maybe someone can come up with something. Okay, so there are a couple of things that we should do before we get to how to choose the best parse. One is, so we filled up this tree, but how do we actually recover the full tree structure of each of these three valid parses? So for those of you familiar with dynamic programming algorithms, maybe you already know maybe what could be done here. Now that we've found three plausible trees using this method. How might we recover the full path, the full tree structure from each of these non-terminals? Any ideas? Yeah. Yeah, that's it. That's exactly what you do. So in each cell where there's a non-terminal, you keep back pointers to the two cells that were used, or in this case, the one cell that was used to come up with that non-terminal. And now, if you have this S1, right, you have a back pointer to this NP and a back pointer to VP1. And then you can follow the back pointer from VP1 back to wherever it spins and so on. Yeah.
I guess in this example, there's kind of clear way that the sentence is played out, like
Mm-hmm.
so what about sentences that have like more clear kind of sentences, that have three different ideas?
Yeah. Yeah, so the question is, what if you have a more complicated sentence that might have like different clauses embedded in the sentence and separated by commas? So the grammar tends to be more complex than what I've shown here. There are non-terminals in the grammar to cover things like dependent or independent clauses and bigger kinds of sentential structures that you might observe in real sentences. So yeah, you can imagine like the parse tree of a very long sentence with a lot of clauses is quite messy, but usually you'll see like each of the clauses will have its own like little parse tree, and it will result in a symbol that's like kind of like S bar is a common one or something like that. And then you see at the high level, these S bars representing each clause will get combined together to form an S. And it basically looks like that. Yeah, so you can actually do a lot of kind of stylistic analysis of a corpus of text by parsing the sentences in the text and then looking at the top of the trees. Like if you just chop off everything except, say, maybe these couple nodes here, you can see, for example, that this sentence is formed by a noun phrase and a verb phrase, so it's a simple sentence. But if you see that there's like a noun phrase, dependent clause, and then a verb phrase, maybe you'll see that this was a more complex sentence or something like that. So that's very useful for a stylistic analysis of sentences. Okay, so the algorithm that we just went through in example is shown here. The important thing to note about this algorithm is that it is cubic in the length of the sentence, so the implementation requires you to have 3 for loops over the sentence. So you see you're looping over the words, then you're basically looping over the words again, like one each cell, and then you're looping over the spans that can be combined to form that particular cell. So all of these are on the order of the length of the sentence, which is why you get this runtime. So it can be quite expensive for longer sentences, but the implementations now have been sufficiently modernized that it's much faster than, say, running a huge neural language model. Okay, so let's get to this problem of how to find the best parse. So currently we have nothing associated with each rule or combination of rules to tell us how probable this parse is compared to this other parse. So in a PCFG, which is a probabilistic grammar, it's the exact same thing, except each rule in the grammar also comes with an associated probability. And there are many ways you can get these probabilities. The most common way is that you have a bunch of linguists take a bunch of sentences and manually create these tree structures using, whatever grammar that they hand create for the task. So there are popular tree banks such as the Penn tree bank, which is created in the 90s and originated a lot of the research on parsing. This tree bank has, I think roughly 1 million words in total, so it's quite small, but it was created like by linguist annotators who were paid to do this task. So given that they created this tree bank, that's what it's called. A tree bank is just a collection of sentences that have been manually annotated with their trees. You can start to estimate the probabilities of each rule by looking at its occurrence frequency in the tree bank. So if there are 10 different ways to form a noun phrase, you can look in the tree bank and see which ways were more frequently occurring than which other ways and assign probabilities just by empirically counting and normalizing over the tree bank, the counts of those rules in the tree bank. So that's the most popular way, but there are other ways. If you don't have a tree bank, how might you get these rules? We'll touch on at the end. One important assumption that's made in this kind of work is that the probability of each rule that's used in the full parse is independent of the probability of all of the other rules. So this is a huge simplification, as we'll see later, but it makes it very convenient to easily compute these probabilities in the chart that we just saw. So here this says that you can compute the probability of any parse by just multiplying the rule probabilities of each rule that make up that parse. So you can compute the probability of a rule in one cell of the chart by just multiplying the probabilities of the cells that were used to combine that rule with the probability of the rule that you're now applying in that cell, as we'll see. So let's try and explain this with the same example that we just used. So here we have the same exact grammar, except we have now probabilities associated with each rule. And these are just like random numbers. They don't really mean anything. So you see here that this rule here has a probability of 0.3, 30%. Again, these rules you can think of as just a subset of the rules in a much larger grammar, so these won't like sum up to 1 for all left-hand side non-terminals and so on. Yeah. Okay, so we're going to just go through the same exact process, except here we're going to keep track of the rule probabilities that we associated with each of the rules used. So in the first level, it's easy. You just like look up whatever the probability of the rule you used was and put it in here. For the other levels, it becomes a little more complicated, but not too complicated. We just have to multiply some things together. So here, I'm forming this NP by combining this determiner with this NP. So there are 3 things that I need to multiply together in order to get the probability for this cell. I need to multiply this probability, 0.9, with this probability, 0.8. So these are the rules that were used before, but these are the ones that I'm using to get whatever goes into this new cell. And I also need to multiply 0.9 times 0.8 with the probability of forming an NP using a determiner and an NP. So this NP on the left-hand side and det NP on the right-hand side. So you can see it here. This is the probability of the rule that we're currently applying in the cell. This is associated with this line here, the probability of an NP being formed by a determiner and an NP. That's 0.3. So this is 0.3. Then we have to multiply that by the probability of the cell, this cell being a determiner and this cell being an NP. So we get 0.3 times 0.9 times 0.8, and we can fill in the probability of the cell as 0.22. So you can see that for longer sentences, we're just multiplying out these probabilities. So we will probably want to work in the log space, given that we could be multiplying a lot of small numbers together. So I can continue to fill out this table. I've switched to log space and filling it out the same way that we went over the first time, except I'm also keeping track of these product of probabilities, or sum of log probabilities. So here, now, this is one of the differences in the probabilistic setting of this algorithm, is that now I have 2 different ways to get an NP. Each of these are associated with a probability formed by like multiplying these rule probabilities together. And this now NP spans an elephant in my pajamas. So the idea here is that I compute the probability of both of these possible NPs, and I find that one of them is slightly higher probability than the other. So one question here, if I'm interested in getting the most probable parse of the sentence, do I have to store both of these NPs in this cell? Any ideas? So my goal is to get the highest, the most probable tree, the most probable S for this given sentence. And so at this cell right here, I have 2 NPs. If I only care about getting the most probable parse, do I need to store NP1, which has a lower probability than NP2? Why not?
I don't think so, because you only ever add stuff to that, so it's not like you're conditioning the probabilities on something else, it's just independent. So
Yep, so exactly, like NP1 is always going to be lower probability than NP2 higher up here. There will never be a parse up here that is somehow more probable when using NP1 than NP2 because of what you said. We're always just adding or multiplying to these probabilities that we've already computed, so there's no need to keep track of this, which kind of simplifies some of the stuff that we have to do in higher levels. Do you have a question? So it really depends. So the question is, with the first version of this algorithm that we talked about, can we discard NP1 or NP2 and just keep one of them? So in the first version of this algorithm, your goal cannot be to find the most probable parse because you just don't have any sort of probabilities associated with the rules. So that algorithm is useful if you're interested in like finding all possible interpretations of the sentence. This one is more associated with if you wanted to, say, rank those or find the most probable one. But you know, if your only goal is to find the most probable parse, there's no reason to keep this. If, on the other hand, your goal is to find all possible parses, then you would want to keep this, and then you could also show that this parse is less probable than this other parse. Oh, here? Oh, yeah. So the question is referring to this cell. Here, okay, so again, when we get up here, we have two different ways of forming a VP. We have this past tense verb with this NP, or we have this VP with this NP over here. So again, we have the same non-terminal being formed two different ways, and we can compute the probability of both and keep the one that is more probable. And then finally here, note that now we don't have three different VPs in the cell, we just have one. So we just have one S token that's formed by combining this NP with this VP. And when we store these back pointers, as you suggest, we can recover the most probable parse by just looking back at where these rules were applied and where the right-hand side is pointing to. Okay, any questions about this? Yeah.
So these rule probabilities, they don't care about the actual semantic meaning of the words further than this part of speech or that part of speech. So, like, is that kind of throwing away a lot of information? Like, we were in a universe where, instead of I shot elephants, like I shot gnomes, I can jump, and gnomes were stealing clothing often,
Yeah. So the question is, these rule probabilities are basically ignorant of the semantic or lexical content of the words that they're spanning. And we are throwing away a lot of information when we simplify the rules to this level. Like, wouldn't it be better to have, a rule conditioned on the identity of the word that's a noun here? So like elephant versus gnome or whatever. Yeah, that's a great segue into this next part of the lecture, where we are taking a look at the major issue of these PCFGs, which is this independence assumption. So each rule probability is independent of the rest of the tree, and we don't take into account the location in the tree or what words are involved in these rules. So like John saw the man with the hat, or John saw the moon with the telescope. They differ in only one word, but the existence of the word telescope should tell you a lot about which structure is more preferred than, for instance, with hat, it's much less clear which interpretation is preferred. And our rule probabilities would be the same in both cases, so that's obviously undesirable. So one way to kind of improve on what we've just discussed is to add more information to the grammar. So we can add different non-terminals that are kind of specific to the head word. So for example, we could have a different prepositional phrase if the noun is telescope. So this could be like PP parentheses telescope or PP parentheses hat, for example, and estimate the probabilities for each of those rules differently, and perhaps that would help take into account some of this information. Common ways are to do kind of informing the current rule based on the identity of the parent, so you can at least get some knowledge about what type of node your parent is, can inform the probability. Regarding what you said, you can get this kind of lexical information into the rules by, for example, this is a verb phrase, fight. This is its own non-terminal in the grammar, only ever used when fight is associated, is like the main verb of the verb phrase. So one question then is, why didn't we just do this in the first place? There are probably some downsides of doing things like this. Can anyone think of some? So of course, this is great, right? We get a lot more information about this verb phrase, and maybe this verb phrase that uses fight has very different syntactic usages than a verb phrase where the verb is like is, right? So that seems generally great, but yeah, so the big problem is sparsity, right? Because now I have like a fixed tree bank. I'm just estimating these probabilities from the occurrence of the rules within that tree bank. How many times do I see a verb phrase with fight in it? Maybe like 2 times or 3 times in my data set compared to how many total verb phrases I see. So I would need a much larger data set that has been annotated with these trees to accurately estimate the rule probabilities of something like BP fight. That said, people do this. There's like a kind of balance that you can reach, maybe like for some popular or high frequent verbs or nouns, you can add these custom non-terminals, but for rare ones, you could even like group them into some category of like rare noun, head word, or rare verb, and then count up the rule probability that way. So that is one thing. There are also ways to get around the sparsity issue by using neural networks. So we know that embeddings have this dense representation instead of like the discrete fight. What if we just replace this with a vector, right? And then we may be able to get around some of these sparsity issues by observing, words similar to fight have similar vectors. So if you're interested in that, there's a line of work that started with this recurrent neural network grammar, or RNNG, where they kind of replace all these rules with vectors from recurrent neural network. This has since been extended to transformer models, yeah, it's a pretty cool line of work. Okay, but yeah, the specific process that we were discussing is called lexicalization. So given the sentence, the lawyer questioned the witness, here, if we lexicalized our rules, we would form, for instance, this NP where lawyer is the head. So this NP is different than this NP where witness is the head. These are completely separate rules. Their probabilities are different. And this S actually is lexicalized with the head word of the whole sentence, which is usually the main verb of the sentence. So you can see this kind of sparsity issue emerging, right? How many times are you going to have a sentence where the main verb is questioned in the past tense? So you have to make some decisions to kind of balance sparsity with the improved information gain that you get here. Okay, so the final thing that I wanted to discuss, and then we can maybe end early, is where do we get these probabilities? So this lecture didn't focus on that at all. The easiest way, which I discussed briefly before, was if we're given a tree bank, we can just compute the maximum likelihood estimate by counting and normalizing based on the rule counts that we observe. So this is very straightforward. If you're interested in getting these rule probabilities without a tree bank, you still have to have a grammar, but once you make a grammar or get a grammar from somewhere, you can use the inside-outside algorithm, which you might have learned about in a machine learning class, to estimate these rule probabilities by, basically you start by randomly initializing all the rule probabilities. Then you use CKY to compute the most probable parse. Now you basically have a pseudo tree bank, right? Because you have used your random probabilities to get parses of each sentence in your tree bank. So now you can compute new counts for these rules using your formerly terrible parser, and you can re-estimate the rule probabilities based on what you just computed, and then repeat this until you get some convergence. So this is a cool way of, it is very finicky to get this to work, but yeah, it's an interesting way to go about getting these probabilistic grammars. Okay, so I guess before we end, I should have done this logistics stuff at the beginning, but your exam grades are released, so you have 1 week to submit regrade requests. We've already got like 30, so I mean, I guess, yeah, please don't submit these regrade requests until unless you're totally sure that there was some error in the grading. As far as remaining deliverables, you will have 1 quiz this week, and that'll be your last quiz. And the homework is due in early May, and then your final project is due May 12th. So that's all you have left to do. If you got a low score on the exam, you should try and put some extra effort into your final project. That's where most of your grade comes from anyway. So I posted some sample grading thresholds on Piazza, which they do vary from semester to semester, but they're mostly around there. So yeah, you can try and estimate your grade using that and see what you need to do. Any final questions? Yeah. So the question is, can we use these like big language models to get better estimates maybe of the probabilities used for parsing? I'm not sure if there's work specifically on that. Usually the people who work on these huge language models are not particularly interested in parsing. There has been some work showing that you can, just by using like prompt-based learning, get pretty good parse trees out of something like GPT-3 with no fine-tuning. So you can show it like, this is a sentence, this is a linearized, because you can make a linearized version of these trees with like bracketing structure to represent the depth and so on. So you can just show GPT-3 like 20 examples of sentence paired with bracketed tree structure, and then give it a new sentence, and it can, I mean, it's not perfect, but it can do a good job at doing parsing, essentially. So, with that kind of result, and also the results that you get on probe tasks, it's clear that these models know a lot about syntax, and yeah, it would be pretty interesting to see if you can tease out these probabilities from them. All right, so see you on Wednesday. We'll talk about semantic parsing then.